Welcome back, my dear students. So in the previous lecture we have discussed about sesquilinear forms, which was the essential tool for describing a bounded linear operator on a Hilbert space, or understanding much about the characterization or generalization of an arbitrary bounded linear operator on a Hilbert space. So using sesquilinear function we can actually characterize a bounded linear operator on an arbitrary Hilbert space. So which was proposed by Riesz, which is called the Riesz representation theorem. So it is formally stated as, so the theorem is that H1 and H2 are Hilbert spaces, and small h, which is defined from H1 cross H2 to K, is a bounded sesquilinear form. Then this sesquilinear form has the representation h of xy is equal to inner product sxy, where s from h1 to h2 is a bounded linear operator, and s is uniquely determined by h and has the norm h is equal to norm s. So if you define an arbitrary bounded sesquilinear form small h from h1 cross h2 to k, it can be uniquely represented by h of xy is equal to inner product sxy, where s is an bounded linear operator and s is uniquely characterized by h, and s and h has the same norm. So if you take an arbitrary bounded linear operator from a Hilbert space h1 onto another Hilbert space h2, we can easily say that this arbitrary bounded linear operator is uniquely characterized by this sesquilinear form H, and using this relation we can easily obtain S as well, and norm of S is can be easily obtained using norm of H, since both of them are actually same. So we have to prove this. So in order to prove this, it is given that H is a sesquilinear form which is defined from h1 cross h2 to k. Now, if it's a bounded linear functional, using Riesz's theorem, we can easily represent S in H in terms of an inner product. So our first objective is somehow convert this H into a bounded linear functional with regards to one of its components, because it has two components. Linear functionals is operated upon single component. So you are fixing some x or y, and with respect to the other component, we are trying to make it as a bounded linear functional, and then using Riesz's theorem so that it can be transformed into this form. So this is our first objective. So for that, consider h of xy conjugate, and this is linear with respect to y, because you are fixing x and changing y. H of x alpha y1 plus beta y2, the whole conjugate, should be equal to, by definition, this is h of alpha, so the h of x comma alpha y1 plus h of x comma beta y2, the whole conjugate. This should be equal to a plus b conjugate is equal to a conjugate plus b conjugate. So h of x comma alpha y1, the whole conjugate, plus h of x comma beta y2, the whole conjugate. Since h is sesquilinear, we can take from the second part, we can take alpha conjugate outside. So this should be equal to alpha conjugate h of x y1, the whole conjugate, plus similarly from here we can take beta conjugate outside. Beta conjugate h of x y2 the whole conjugate. Now alpha conjugate the whole conjugate is alpha. So alpha times h of x y1 conjugate plus beta conjugate the whole conjugate is beta. Beta times h of x y2 conjugate. So using this relation we can easily say that our h of xy conjugate is a linear operator with respect to the second component y. So now what we are going to do is we are fixing x. So fix x. Then h of xy for every fixed x h of xy conjugate is a bounded linear functional. Because this is linear with respect to the second component and it is already given that h is bounded. So this is bounded and linear functional. We are fixing x. Now using Riesz's theorem, every bounded linear functional can be represented in the form, here y is the variable, so it can h of xy conjugate can be written as some g of y. Okay, here y is the variable, x is fixed. By Riesz's theorem, g of y, which is h of xy conjugate, can be written as inner product yz for some z, which we have already done. Now this should be equal to inner product zy conjugate. So taking the whole conjugate, so we can write h of xy should be equal to inner product zy. So h of xy somehow is written in the form inner product zy. This representation is obtained since x is kept fixed, h is linear with respect to the second component. Using Riesz's theorem, this form is possible. Now use the property of inner product. Now we have obtained like this, where x belongs to the first component and y belongs to the second. So x belongs to h1 and y belongs to h2. Now since x is fixed, this operation is being carried out on h2. Okay, so this h for a fixed x is a bounded linear functional from h2 to some k, and it can be represented as inner product zy for all y, and z is an element in h2 because we are operating on h2, because the first component is in h1 which is being kept fixed, which is not at all changing. So this z is actually in h2, which corresponds to some fixed x element of h. So what we have done is we have fixed an x element of h1. Associated with this x, we have defined a linear operator and we have found a unique z which belongs to h2. So corresponding to each x element of h1, we can actually define an z element of h2. So thus we have an operator which maps an arbitrary x element of h1 onto an arbitrary z element of h2. So thus S, which is defined from h1 onto h2, is an operator which is defined as x is equal to z. So if you substitute that h of xy was defined, well, inner product zy, z is sx, so this is sxy, where s is a operator from h1 on to h2. Now we have to prove that h is a bounded linear operator. That's what we have to prove. So we have obtained the form of h. H should be of the form inner product sxy, where s is a function from h1 on to h2. Now we have to prove that s is linear, bounded linear operator. If that happens, we have successfully established the result. So now, to show that S is linear, for that, take S of alpha x1 plus beta x2, where alpha, beta scalars, x1, x2 elements of h1. So we have only one information regarding S, that is h of xy is equal to sxy. So in order to establish the linearity of this, we have to operate on this. So we have to prove that this should be equal to alpha sx1 plus beta sx2. So in order to do that, take this inner product s of alpha x1 plus beta x2 comma y, which by definition is h of alpha x1 plus beta x2 comma y. Since h is a sesquilinear form, it is linear with respect to the first component. So this is h of alpha x1 y plus h of beta x2 y. So this should be equal to alpha times h of x1 y plus beta times h of x2 y. Which by definition is h of x1 y is inner product sx1 y. So alpha times inner product sx1 y plus beta times inner product sx2 y by the definition of h. Now this can be taken inside. This should be equal to inner product alpha sx1 y plus inner product beta sx2 y by the property of inner product. Now again using the property of inner product, this is alpha sx1 plus beta sx2 y. Now we have already established that for every w, inner product v1 w is equal to inner product v2 w. For all w implies v1 is equal to v2. This is true for all y element of h2. Now we have proved that inner product s of alpha x1 plus beta x2 y should be equal to inner product alpha sx1 plus beta sx2 comma y. So using this lemma, we can say that s of alpha x1 plus beta x2 should be equal to alpha sx1 plus beta sx2. So s is actually linear. Now we have to prove that s is bounded. S is bounded, and we have to establish that norm s is equal to norm h. So if s is equal to 0, we have nothing to prove. Clearly 0 operator is bounded. So we consider the case when s is not equal to 0. We have norm h should be equal to supremum x element of x minus h0, y element of, or this is h1, this is h2 minus h0, modulus of h of xy divided by norm x times norm y. So this is equal to supremum. We say x not equal to 0, y not equal to 0. H of xy is inner product sxy divided by norm of x times norm of y. Now this is true for every y. So in particular, we choose y is equal to sx. So this is, if we are, this is the supremum over all values of y. Now if we take the particular value y is equal to sx, the value of this should be less than that, less than this quantity, because here we are taking supremum over all x and all y. So in the next case, we consider y is equal to sx. So this should be greater than or equal to supremum x not equal to 0. We take y is equal to sx modulus of inner product sx divided by norm x times norm sx. Now this second part should be equal to supremum x not equal to 0. This is actually equal to norm of sx the whole square divided by norm x times norm sx. So this is actually equal to supremum x not equal to 0 norm sx divided by norm x. Because s not equal to 0, we can cancel norm sx. This by definition is actually equal to norm of s. We have started with norm h. So norm h, using this inequality, we can easily obtain that norm h is actually greater than or equal to norm s. So norm h is actually greater than or equal to norm s. Or norm s is less than or equal to norm h. This is a fixed number. So which means that this proves that s is bounded. Okay. So s is bounded. So now we have to prove that norm h is equal to norm s. So one of the part has been already proved. We have already established that norm h is greater than or equal to norm s. Now we have to prove the reverse part as well. So to proving the reverse part, we consider norm h. So norm h should be equal to supremum x not equal to 0, y not equal to 0, modulus of in h of xy, which can be written as inner product, modulus of inner product sxy divided by norm x times norm y. Now by Schwarz inequality, this upper hand side should be less than or equal to norm sx times norm y. So this is less than or equal to supremum x not equal to 0, y not equal to 0, norm of sx times norm y divided by norm x times norm y. Since y not equal to 0, norm y should not be equal to 0. So this is equal to supremum x not equal to 0. We cancel norm y, norm of sx by norm x. So this should be equal to norm s. So this implies norm h is less than or equal to norm s by equation number 2. So from equation number 1 and 2, we can clearly write norm h is equal to norm s. So we have successfully proved that our S is a bounded linear operator. So every SQL linear form has the representation h of xy is equal to inner product sxy, where S is a bounded linear operator and h is uniquely determined by S or vice versa, and both has the same norm. So every bounded linear operator which is defined from an arbitrary Hilbert space onto another Hilbert space can be uniquely characterized by a SQL linear form in general or vice versa. Okay, thank you. This is called the Riesz representation theorem. Thank you.